Next, I want to cover how the shortwave energy from the sun interacts with the Earth as it's making its way through the atmosphere and also striking the surface of the Earth. So it's maybe at a really basic level, the concept of absorption and reflection. So here, this person has a dark jacket on while they're skiing, and this person has a light colored jacket on while they're skiing. And you can imagine which one is going to warm up the most. It's going to be the dark colored one because dark colors will absorb more energy from the sun, where light colors will reflect more energy from the sun. So that's kind of a real basic level. Also, one thing you might note is that this might be a day when the temperatures are quite warm, yet the snow is not melting. And the snow is maybe not melting because, like the jacket, it is also reflecting energy from the sun. So it is not absorbing that sun's energy, causing it to melt. So while we have incoming shortwave radiation from the sun and outgoing long wave, as we've mentioned, there's also interactions with this energy from the sun, that a portion of it is reflected back out into space without warming the Earth, kind of like when it strikes the snow. In fact, there's a much more complicated pattern that we won't go into full detail on, but a lot of things happen to the sun's energy as it's making its way through the atmosphere and striking the surface. Some of it's absorbed by clouds, some of it is scattered by dust, some of it is reflected by clouds, and some of it is reflected by land surfaces. So let's break this down to a few kind of easier to digest terms. So we're talking about the pathway of that shortwave energy from the sun to the Earth. What happens to it on the way? One thing I want you to know is a term called insolation. And that's a kind of shortened version of incoming solar radiation, insolation. It's unfortunate that it sounds like something that you would put in your attic to warm your house, but it's spelled differently. Sol, like solar, like incoming solar radiation. This is that incoming shortwave energy from the sun. And a few things can happen to that energy as it's making its way through the atmosphere and striking the surface of the Earth. One is it can be scattered in the atmosphere. So little particles of water or other matter in the atmosphere, nitrogen, what have you, some of the light can hit those and scatter off in a different direction. That's called scattering. We'll come back to scattering in a moment. Scattering is one of the reasons why we have different colors of sky, why we have a blue sky, red sunsets. A lot of that is related to scattering. The other one is reflection that we mentioned a moment ago, where lighter objects will be more reflective, including clouds, and darker objects will be less reflective. And also, while we're talking about reflection, it's also a concept called albedo. Albedo is the percent reflection happening by different objects. So reflection is energy just being bounced right back to space without being absorbed or warming the Earth. And then lastly, kind of like the white jacket in the ski scenario. Then lastly, the energy that is not scattered, not reflected, can be absorbed, and it's the remaining energy that's absorbed and warms the Earth. So this is part of a complex energy budget where we have shortwave energy coming in from the sun, and we kind of made it very simple. We have shortwave coming in and long wave going out. But you should be aware that there are there's different interactions happening with objects on the Earth and in the atmosphere, both with that shortwave energy and also with that long wave energy. For example, the greenhouse effect that we mentioned earlier. So you have, whatever amount of units coming in from the sun, some of that is absorbed by the Earth's surface, but a big portion of that can either be reflected or kind of absorbed in the atmosphere. And different objects are going to have different level of reflection. So this is a figure showing albedo. Albedo is how much, what the percent what percent of the energy is reflected. And I'll contrast two objects here. Snow has high albedo, very reflective. 80 to 95% of the energy that strikes snow is reflected back out in space. That is a reason why you can have snow that stays in solid form even when the temperatures are above freezing, because it's not absorbing that solar energy. Part of the reason why it has such high albedo, one, the color, the bright color, and also the texture. It tends to be a very flat surface, making the energy very easily to bounce off of it. By contrast, forests have very low albedo. Forests are darker in color, and they also have more texture. They have a lot of leaves and branches, places where the light can bounce around and have more opportunity to be absorbed. So forest is low albedo, snow is high albedo, more reflective, less reflective. Now, one thing I want to stop, pause, and note, though, that when it comes to reflection, the thing in the Earth system that reflects in more energy than anything else is clouds in the atmosphere. More than land or water on the Earth, that reflection from clouds clouds are the primary reflector on the Earth's surface. So this is a figure showing how much albedo is happening in different places. Here near the equator, especially with the water, very low albedo, that water is very absorbing. When you have the ice near the poles, that has very high albedo. This is showing how much energy is being absorbed by the sun over the course of the year at different latitudes. Here at the North Pole, remember the North Pole is in darkness for 6 months. So, and when it's in light, it goes up pretty high to the summer solstice, and then it drops back down, and then it's kind of absent for the rest of the year. Around 45 degrees north, that'd be about Northern California approximately. Here you have a real seasonal pattern where you have some but less because of the low sun angle in the winter, more with the more direct sun angle in the summer, and then going back to less again. So this is a kind of mid-latitude seasonal pattern. Now here at the equator, you're in the tropical zone where the sun is always going back and forth overhead. So you have this weird pattern where it's kind of a little higher, a little lower, but it's fairly consistent, right? Because the sun is always kind of going back and forth overhead over the course of a year. Now, we talked about different wavelengths, and we kind of grouped visible light all together, but one thing I do want to point out is that within visible light, it is a spectrum, and from all the colors of the rainbow, but these are the three primary colors that we see. Our eyes are adapted to see reds, greens, and blues. Right? Red is the the longest wavelengths are reds. You can see the longer wavelength here. And the shortest are the blues, going into what we perceive as violet. Now, so as sunlight, which is visible light, goes through the atmosphere, it's going to have, part of it's going to be red wavelengths, part of it's going to be green wavelengths, part of it's going to be blue wavelengths. And there are going to be particles, sitting in the atmosphere. So if you had to bet money on which one of these, the red, the green, and the blue, is going to hit more particles as it's going through the atmosphere, which one would you put your money on? Taking a look at it. Now notice that the red is long and it snakes really long. So it can kind of weave its way around more particles than the blue, which is kind of wiggling much more back and forth. So the point of this is, statistically speaking, the blue is much more likely to strike particles in the atmosphere than green or red. Red is less likely, blue is more likely. And that's why why the sky looks blue, because as these wavelengths of light are traveling through the atmosphere, the blues are bouncing off of things more than the other colors are. And because the blue is being scattered more than the greens and the reds, we see that scattered light overhead as blue. So that's why the sky is blue. For different reasons on sunset, more of the blues get scattered away in the greens, leaving more of the kind of yellows and reds, or kind of the leftover light that gets to you. So without making it too complicated, the reason why the sky is blue and the reason why we have color sunsets is because of scattering. So scattering is related to different sky colors, both blue sky overhead and when you're at a longer angle, the kind of non-blue sunsets.